Hi, I'm Dan Abel, and in this lesson, we're going to learn how to draw electric field lines created by two charges. If we want to draw the electric field lines created by two charges, we have to keep in mind that the electric field created by each charge is a vector. And so that means that it's got a magnitude and a direction, and we can get the total field by adding the individual fields using vector addition. Let's see that vector addition in action. For A here, we're asked to draw the electric field from a pair of charges, one positive and one negative, 1 coulomb. And it helps when doing this to pick a few points of interest and use that to help sketch it out. So here are our positive and negative charges. And I'm just going to pick a few places to look at what the field looks like. You can pick additional places, but once you kind of have a sense of what the field looks like, you'll be able to draw it without having to go through this test case. So let's start with this top point. And if we look at that top point, the field from the positive 1 coulomb charge is going to repel that point. Because remember, physicists are positive people. This is a positive test charge. So we'll get a repulsion, and the electric field from the positive 1 coulomb will look like this, pointing up and to the right. And the electric field from the negative 1 coulomb, that'll be attractive, will be pointing down and to the right. And if we add these as vectors, the up and down components, the vertical components cancel, we end up with a total field that's completely to the right. If we look at the middle point, again, the field is pointing to the right from the positive 1 coulomb charge, pointing to the right from the negative 1 coulomb charge. We add these as vectors, the total field is double, since I have two rightward pointing fields at that location. And then if I look at point 3, it looks like a mirror image of the first point. We end up with the same one field being repulsive, one field being attractive, vertical components cancel, and our net field is to the right. Now notice our strongest field is in the middle, which makes sense because that's where I'm closest to the two charges. Should have the strongest field at that point. And if we continue to do this, we would get a total field picture that looks like this. Now let's take a look at part B, where we've doubled the size of the negative charge. So we've gone from -1 to -2 coulombs. And what's that going to change? Well, if we look at our original field vectors from the negative charge, they're all going to get bigger. So the contribution to the field from the positive charge is not changing, but each of these negative charge field vectors is going to get larger. So we're going to have twice the amount of pull towards that negative charge. And so when we go to look at the total field, it's going to be imbalanced with a larger field density towards that -2 charge because, as we've seen previously, and as we're reminded in this lesson, the density of field lines, the number of field lines, is directly proportional to the strength of the field at that point. Now let's look at what happens when we have two of the same charge, um, a +1 and a +1 coulomb charge. You can see that this field looks a little bit different. The combined field from these two charges in the middle looks like it pushes away from each other. And this is because of the combined effect, the combined repulsion of these two charges on any positive charge placed in the middle here. So for example, if I place a positive chest charge up here, it's going to experience two field contributions. One from the charge on the left, which is going to push away, and one from the charge on the right, which is going to push away. And so if I add those fields as vectors, I end up getting a total field that is straight up at this point. And that matches the combined field that we see in the picture. And we can keep going. We can do this exercise at all the points here, and we'll end up seeing that that's where this pattern comes from. But you want to remember that if you have two of the same charges, they will produce a combined field that does not connect because field lines cannot cross each other. And if you have two of the opposite charges, you will produce a field that at least some of the lines connect one charge to the other. So the big takeaway when you want to draw an electric field is to think about the contribution from each charge at a specific point and then add them as vectors. And then do that at enough points to where you get an overall sense of the direction of the total field.